Have you ever stopped to wonder what really separates a luxurious melt-in-your-mouth chocolate bar from one that's just kind of chalky and disappointing? Well, it's not just about the quality of the cocoa beans. It's a hidden science, this incredibly precise dance of molecules that has to happen long before that chocolate ever gets to you. Today, we're going to dive deep into the crystal science of chocolate tempering. So yeah, what is the secret? What makes a chocolate bar perfect? It all comes down to one thing: how the fat inside the chocolate, the cocoa butter, turns from a liquid back into a solid. If you control that process just right, you get perfection. But if you get it wrong, well, you get something very, very different. And you know the difference the second you see it, right? The best chocolate has that gorgeous, shiny gloss. It has a sharp, satisfying snap when you break it. And of course, it melts perfectly and smoothly on your tongue. The worst, it looks dull, it's kind of soft and crumbly, and sometimes it has that weird whitish film on the surface. That's called fat bloom. And this isn't about expensive versus cheap chocolate, not really. It's all about structure. So here's our game plan. First, we'll uncover the secret behind that snap. Then we'll meet the 6 different personalities of cocoa butter. After that, we'll learn the 4-step temperature dance, peek inside a factory tempering machine, figure out how chocolatiers read the results, and finally, solve the mystery of that pesky fat bloom. All right, let's get right into it. That amazing snap, that beautiful gloss, it all boils down to one critical process: tempering. And tempering is simply the art of controlling how fat crystallizes. Now, I know that sounds super technical, but here's what it really means. Tempering is basically persuading trillions and trillions of tiny fat molecules to line up in one specific, perfect pattern. We do this with a very controlled process of heating, cooling, and stirring, which creates these things called seed crystals that act like a blueprint for the rest of the chocolate to copy. So why go through all this trouble? Well, it's because cocoa butter is what scientists call polymorphic. It basically means it has a secret superpower. It can solidify or crystallize into 6 totally different structures. And trust me, each one behaves very differently. The easiest way to think about it is like a ladder of stability. At the very bottom, you've got form I. It's super loose, unstable, a real mess. As you climb that ladder, the forms get more and more organized, dense, and stable, all the way up to form VI. The higher you go, the more tightly packed those molecules are, and the higher the melting point. Our whole job is to land on one very specific rung of that ladder. So let's focus on the 3 main players here, kind of like characters in a story. You've got form 4, the unstable imposter. It makes the chocolate soft, gives it no snap, and it's the one that causes problems later. Then there's form V, the gritty villain. It's actually too stable. It can form during long-term storage, and it makes the texture feel grainy. But form V? Form V is our hero. It's the holy grail. Its unique, tightly packed structure is what gives chocolate everything we love. The hardness, the gloss, the snap, it's perfect. Okay, so we know who our hero is, form V. The big question is, how do we make sure only the hero shows up to the party and none of those other characters? The answer is a very precise choreography of temperature changes. We call it the temperature dance for a reason. It's not random. Every single step has a very specific purpose. First, to wipe the slate clean of any old crystal patterns, then to create a brand new mix of crystals, and finally, to selectively destroy the ones we don't want, leaving only the perfect form V crystals behind. Here's how that dance goes, in 4 steps. First, you heat the chocolate all the way up to around 50 degrees Celsius. This is like hitting a total reset button. It melts every single crystal. Step 2, you cool it down to about 27 degrees Celsius to strike seed. This forces a whole mix of crystals to form, both the good ones and the bad ones. Step 3 is the real magic. You gently reheat it to just around 30 degrees Celsius. This temperature is high enough to melt away all those unstable imposter crystals, but it's just cool enough to leave our hero, form V, totally intact. And just like that, you've got perfectly seeded chocolate that's ready to use. Now, that process is perfect if you're making a small batch in a kitchen. But what if you need to make thousands of chocolate bars an hour? You can't exactly use a spatula and a marble slab for that. That's where some serious industrial engineering comes into play. This right here is an industrial tempering machine. It's basically a vertical stack of super precise temperature zones. Chocolate gets pumped through it, going through that exact same heating and cooling dance we just talked about. But these machines add another crucial element: high shear. That's just a fancy way of saying intense mixing. This stirring action breaks up the crystals into millions of tiny seeds very, very quickly, which is absolutely essential when you're dealing with huge volumes. In the industrial world, this leads to two main ways of doing things. You've got conventional tempering, the classic method we just described, where you create the seed crystals from the chocolate itself. But there's also a really clever shortcut called seed tempering. Instead of making your own seeds, you just add them. So with this process, you take untempered liquid chocolate, cool it down just a bit, and then you mix in a tiny amount of a special suspension that's already loaded with pure, perfect, stable seed crystals. This gives the rest of the chocolate the perfect blueprint to follow, and it leads to an incredibly reliable temper every single time. It's just a more direct and often more consistent way to get the job done. Okay, so the chocolate's gone through the machine. It looks ready. But how can a chocolatier be 100% certain they've nailed the temper before they start making 10,000 candy bars? Well, they use a special device called a temper meter. It's a really cool quality control tool. It takes a small sample of the chocolate, cools it down under very specific conditions, and then it plots a graph of its temperature over time. The shape of that graph, which is called the cooling curve, tells you absolutely everything you need to know. This is the curve you want to see. This is the money shot. In a perfectly tempered chocolate, as it cools, all those seed crystals cause a massive, rapid crystallization. Now, that process actually releases a little bit of energy as heat, and for a few critical moments, the heat being released perfectly cancels out the cooling from the machine, creating this distinct flatline or plateau. That flatline is the signature of success. But what happens if you don't have enough good seeds? Well, that's called under-tempered chocolate. In this case, the cooling process is stronger than the crystallization, so the temperature just keeps dropping. It creates this characteristic dip in the curve before it finally starts to level out. Seeing that dip is a clear warning sign that you need to adjust the process. And then, of course, you can have the opposite problem, too many crystals. This is called over-tempered. Here, crystallization happens so fast and so intensely that the burst of heat actually overwhelms the cooling, causing the temperature to spike upwards. When this happens, the chocolate gets way too thick and becomes really difficult to work with. This meter lets chocolatiers see exactly what's going on and fine-tune their machines in real time. Which brings us right back to where we started, that sad, chalky-looking chocolate. Now that we understand all these different crystal forms, we can finally crack the case of fat bloom. At its core, fat bloom is just a transformation. It's what happens when poorly tempered chocolate is full of those unstable Form 4 crystals. Over time, especially if the temperature fluctuates, those unstable crystals will always, inevitably, try to reorganize themselves into the much more stable but gritty Form V6. So think of it as a chain reaction. Poor tempering leaves behind those unstable crystals. Over time, those crystals start to change into the gritty Form V. As the molecules repack themselves into this new, denser structure, they actually squeeze out liquid fat that was trapped between them. That fat has nowhere to go but up, so it migrates to the surface, where it solidifies into those big, visible blotches. That's what gives the chocolate that dull, whitish look. It's totally safe to eat, but it ruins the texture and appearance, all because the wrong crystals were left behind at the start. So, from the beautiful gloss and sharp snap to that perfect, smooth melt, pretty much every quality we love in a chocolate bar is decided by this completely invisible architecture. The next time you break off a piece and you hear that satisfying snap, maybe you'll think about the incredible, invisible dance of crystals that had to happen just right to make that simple pleasure so perfect.
Industrial Bakery Simplified.